Hello.
Yes.
Welcome to this morning's seminar. It's my pleasure to introduce Maike Sonnewald as our guest speaker. Maike got her PhD in physical oceanography from University of Southampton and in complex system simulations. She continued that to get a PhD from Southampton in complex system applied to oceanography. She's currently a visiting scientist at the University of Washington, and she's a postdoc at Princeton, scientist at Princeton as well. And you're somehow affiliated with NOAA too.
Just to make it more complicated.
She wears many hats. Maike's focus is on ocean and climate dynamics. She has pioneered machine learning methods to learn about the system, and her core motivation is to deliver actionable information to decision makers. The focus is on physical and biological oceanography. She's passionate about bringing the different branches of oceanography together. She has contributed mightily for a young scientist to the advancement of the ocean and its data science, and part of her contribution includes review articles, a lot of invited talks, and we are very happy to have her here.
Thank you.
Take it away.
What I'm about to tell you might be unexpected, but it's actually true, and that is that large language models like ChatGPT, their most important contribution and the revolution that they create in terms of searching the internet for us is actually not going to be what we care about. It's going to be how we use machine learning and data science to actually advance our understanding of the fundamental process and how we deal with challenges that face us through climate change. And today I'm going to be demonstrating to you that the innovations and the fundamental insight that I've been able to create has only been possible because of my very interdisciplinary background that Mo just mentioned. And I have a physical and also a biological aspect to my work where I focus on actionable information for decision makers. Today I'm going to be talking about some of the physical aspects of my work, but my work has impacted national and international policy, is also featured in national and international climate model improvement, and I'm cited very broadly from malaria research to clinical neuroscience and of course also oceanography. So I have a foot in both the data science and also the oceanography part and this exciting interface in between. And it's worth highlighting that data science and computational science really has a long history in geophysical fluid dynamics, or GFD. And here you can see a picture of the ENIAC computer. This was first designed for geophysical fluid dynamics problems as well as chaos theory. All of this was born with us. And I have a range of different interests, but today I'm going to be talking to you about large-scale ocean physics, specifically the overturning, and be jumping in and out of different data science methodologies that I hope to excite you about. But overall, I want to impress on you that injecting knowledge to solve hard machine learning problems really goes hand in hand, and we can make a lot of progress together. But just because I know the audience, specifically also online, is somewhat mixed, I want to make sure I carry everyone with me. So just to define quickly, unsupervised learning and supervised learning are two of the branches of machine learning that we'll be covering, where unsupervised learning doesn't have labels. So the upper left plot doesn't have any colors in it, so you can think about this as temperature and salinity, for example, or axes. And every dot here, for example, is a point of latitude and longitude. And if we want to develop an unsupervised model, what we do is look for covariance, significant covariances within this data set, so denoted in these colors. But if we have supervised learning, the bottleneck really is having good labeled data, where you can see the bottom left now has colors. And what we're trying to do is draw this decision boundary, so this green line, and really just note how important having good labels are, because here we're just sort of clumping three of the important parts together. And the supervised aspect is what's often called a black box, so you do this a lot of the time with tools like neural networks. But now for the other part of the audience, here's a very cartoon version of the ocean where the warm surface currents are in red and blue is cold, and you can see that in the North Atlantic we have currents going up sort of nicely sandwiched between the different continents. And in the Southern Ocean, I want to highlight that we have this ocean around Antarctica zooming around, and this is the Antarctic circumpolar current, where waters are also being brought up. And those are the two features that I'll be focusing on. But of course, it gets a lot more complicated, and this is just a snapshot from a high resolution model where the colors represent the temperature of the surface currents. And really looking at images like this, you can see that there are patterns and that there are emergent features even on these types of scales, but actually understanding what makes them emerge is something that I'm very interested in. And this is of course something we also do in data. And within this space, I really want to highlight that we're in a revolution of available data. It's really a very exciting time to be an oceanographer, where new tools are going to highlight different important areas and also lead to new discovery, where, for example, the Argo data set is just fantastic. But today I'm going to be confining myself to numerical models largely. And to just highlight what they do for the different audience here, numerical models solve what's called the primitive equations. I'm just showing you them there to the right, just to show that they are very interesting and beautiful, but also somewhat nasty second-order nonlinear PDEs with an intractable number of fields approached naively. And I think it's fair to say that progress using traditional methods like linearizing or brute force simulating isn't going very far these days. And the problem that I'm tackling here is that the nonlinearities are missing. So what I'm very proud to have been part of is really pushing this frontier of how we can use advanced computing around this. And what we do, why this is hard, why brute force simulation is difficult, is because we have to discretize, and all scales need to be represented. So for example, on the sketch there of a climate model to the right, you can see we have all these little boxes, and that means that we've made choices about what we can actually see. So imagine my face, if I'm pixelated by 4 pixels, you can't really see, for example, that I'm wearing glasses probably. And that might be important, it might not be important. But in a climate modeling context, of course, we have to make choices. And for example, in the ocean sketch on the bottom left, for a given way of representing these equations, the primitive equations, we have made choices, but in each box we have access to all the information that let the circulation emerge. But it's worth highlighting from a data perspective that each grid box for a model I'm working with has approximately 39 fields. And the typical grid box numbers in also what we call forced resolution or low resolution is really formidable. And as we move to higher resolution, which we want, this gets to be an even bigger problem. And to highlight what this means in a climate modeling context, we really need to understand what physics that are key we're lacking. Because here you see a figure of an empirical analysis of the CMET models, and I'll be getting back to these. The blue error bars here show you what's due to model uncertainty, so what's due to the physics that we're representing in a way that isn't really well captured across the ensemble. And notice we're doing pretty well at the start here, but then this error spreads. So today I'm going to be talking to you about a few different case studies. So first we're going to determine key processes, and I'll be using the Southern Ocean circulation example. Then I'm going to be showing you how we can infer subsurface circulation, and I thought for this audience taking a North Atlantic approach will be nice. And then we're going to be looking at how we can ensure safe and transparent methods. But before jumping in, I want to invite you to close your eyes and imagine that you're listening to a piece of music you know very well, played by a 200-piece orchestra, and you're looking for maybe just a little instrument like the fourth piccolo. And this is really important, it adds that extra note. But actually hearing it and knowing what its contribution is to this piece of music is really hard. And in the ocean we have so many things going on that we really have overwhelming complexity that stymies progress. And the grand challenge that I'll be illustrating how I'm working with today is finding patterns in complex data, but importantly for causal understanding. And what do I mean with this? Why is this different? How can we be rooted in equations, these primitive equations? And going back really to the fundaments of how we make scientific progress, we do this through having testable hypotheses. And traditionally, we take data on existing knowledge and determine patterns. But this existing knowledge part means that almost per definition, you're subjective. So if you look at the example here to the right, we have a cannonball being fired up and then fired down. And if you were just to observe this, you'd say, okay, I have a gravity-dominated and a less gravity-dominated area, but that would be somewhat misleading if you're looking for those underlying systems. And here, my innovation has been to use machine learning to determine hypotheses for me. And these little light bulbs are, again, because I know the audience is a little bit spread, this is where I've contributed with an innovation. And overall, what we can do here in terms of making progress from an oceanographic perspective is that machine learning can simplify and explain things with parsimonious equations. So understanding where certain terms are important. And I call these dynamical regimes, where traditionally, if you're looking at different balances of drivers, you might start with something along the lines of what's to the right, where here we've just chosen an arbitrary streamline to say this is the gyre, and here you're looking at the North Atlantic. And this, of course, is something that I'm going to demonstrate that we can do much better. And to do this, I use the estimating the circulation and climate of the ocean, or ECHO, at 1 degree. And ECHO is a fabulous data product in the sense that it takes a model, but then it also fits itself to existing data. So it takes this into account, which means that working on the resultant fields is very interesting because it's tied to observations. Now what do we do with this? I take the full fields for momentum and then perform what in data science language would be a symbolic transform, and move this from, remember what for just momentum was 39 different fields and we have 75 depth levels, to 5 dimensions that are also interpretable. So I move it into a space that's called the barotropic vorticity space, or the barotropic vorticity space, working on a budget. And I have 5 different terms now that take the full baroclinic ocean as it's realized by this ECHO model. So I'm really not leaving anything out, but moving it into a different framework. And the 5 terms are the advector component, to do with being on a spinning sphere, the bottom pressure torque, so interacting with the seafloor, the wind and bottom stress, so effectively the wind pushing against the top, the nonlinear torques, and the lateral viscous dissipation. And on the bottom, I'm carrying these little cartoons with me because I know that the equation terms might not be as intuitive to other people. But remember what we would traditionally do, just drawing a streamline and saying, hey, how do these different terms balance? So for example, in the Southern Ocean, you might just draw a ring around where you see the wind stress being intense. And I'm going to be demonstrating how we can do this differently, because what we're asking is, are there patterns in these terms? And this is a clustering problem. This is something where we can use data mining. So what did I do here? I started first from a data science perspective very naively. I fit a model, the k-means model, and K here stands for how many clusters am I looking for? How many different bits do I want to chop this data set into? And we can rely on very established statistical methods called information criteria values. And here, the lowest number I could get away with was around 50. And this was great from a data science perspective, but it failed for oceanography. Because if I was looking at cluster 35, then it would move around. So the thing that I cared about, can I find the same part of the ocean, wasn't represented, viewed naively. So what I did was go and define a new geoscientific criteria to be able to consolidate this. And this is effectively physics-informed learning theory. So I injected that oceanographic knowledge. And what does this look like? The 6 different dynamical regimes that govern the world ocean are expressed there on the left, where, for example, some areas like the pink regions drop out and deliver something in your lap that, as oceanographers, we've been thinking about for a very long time, since the 50s. For example, the Sverdrup balance. So if you look at the bars there to the left, to the right, you can see that the pink bars have a balance between the wind stress and the planetary vorticity advection, And this is what I know, it's theorized, but now I can draw the actual boundaries. And in the Southern Ocean as well, something really unexpected popped up, which is the Southern Ocean regime, where we have this incredibly intense balance of terms, and I invite you to go look at the cited publication to the right to learn more. But overall, we have these things that we recognize, but I'm going to be going into a case study now about this area where we learned something new, and this is in Press and Nature Communications, Earth and Environment. But just to highlight, we've gone from something that's really a lot more sophisticated and that we can do very different work with. So now jumping into the Southern Ocean, it's worth highlighting that the Southern Ocean really connects the world, because here I'm showing you the ocean circulation, but centered around Antarctica now in the middle. And in the North Atlantic, we have these currents going up, but remember we had this pink area that also actually is what's called a wind gyre, so it has clockwise circulation in the northern hemisphere. We don't have that in the Southern Ocean, but we still have the pink regime cropping up. So what's going on here? And the subpolar gyre, the ones around Antarctica, are also very important because they modulate the upwelling. And this is a very important component of the climate system. And traditionally, two regimes are seen as key in the Weddell and Ross Sea. But now, if we go in and use these dynamical regimes, I can say, okay, there's definitely the pink regime, but in the Ross and Weddell Sea, there's nothing special. So what's going on? I was really expecting to have the pink regimes crop up in these areas, but I'm not seeing them, and that is really interesting. Because remember, we don't have the continents, and the continents are really important in the North Atlantic because they create dissipation on the western side to allow this gyre circulation. But in Antarctica, around Antarctica, we have very rough bathymetry, and that's what I'm showing you a map of here, but it's definitely not zonally symmetric. So what I can do now is go back to these terms, and instead of just drawing a ring around the wind stress, I can go in and say, okay, in this pink region, if I extract these terms as I'm showing you on the bottom right, what does this look like? In the Southern Ocean, I can see that, or in the Southern Ocean regime, sorry, I can see that it's picked out these areas that are very intense in terms of the wind. And in the nonlinear regime, I can see that I have intense dissipation, and this is this term denoted by the little dragon. And this now lets me reevaluate what I thought I should see. And to demonstrate this, I'm just picking a mountain range because remember that the topography is really intense. So if we pick this out and just draw a little sketch, we have dramatic topography and then less or no dramatic topography. And if we now have the Antarctic circumpolar current coming in, it hits this mountain range and is deflected, and this causes dissipation. And that means that some of the flow can transition into a different state, and then as it's hit by the wind, have this gyre circulation happen. And if you look at the fields and if you search for this, it pops out at you. And I would propose a supergyre to rethink how we're looking at the Southern Ocean circulation. And having posed this, and I invite you to go look at the paper for a lot more detail, but I propose that we have a series of leaky subgyres, and that the thing we really need to pay attention to is, where does the topography end? And if we look at this, really we can explain a lot of features that are important for this area. And preconditioning of the flow to understand what's happening is really important. So if, for example, you're looking at the Ross gyre and trying to understand, okay, how do warm currents come in on the side here, then really you need to be aware of what the rest of this area is doing. So I posit that the implications for this, and I should also say that if you then go back and reevaluate some of the observations that we have, even back in the 80s, we see these features, and this is really exciting. So we have a quasi-circumpolar, zonally asymmetric supergyre that modulates world climate through this upwelling. And the way that we've traditionally made progress on this is very idealized. Largely theory is 2D and has very idealized versions of what topography is. And of course we know from this analysis that could be actively misleading. So the implications are that the upwelling, if we just focus on these two regions, could be underestimated. and that this new framework, showing us where to look, might be able to guide observations. And in the context of the next section, I'm going to be going into that a little bit more. But now, just to highlight, this was at low resolution, 1 degree, and we know that, of course, there are a lot of other processes that we're very interested in at higher resolution, but this now, in terms of data science, becomes a formidable challenge, and not just because the data is large, no. It's because it's also intensely nonlinear and unbalanced. So we care about very small parts of the system because they, for example, produce this downwelling of very dense waters in the Southern Ocean. So really, conventional methods here fail even more. So new methods are needed, and this is where my work comes in again, more from a data science perspective, in the sense that I recognize what tools I need. So here I'm introducing the native emergent manifold interrogation method, or NEMI for short, where a paper describing this in detail is currently in review, but it's freely available on GitHub, where I pull from graph theory and a number of different tools, and then combine this with domain knowledge to be able to create utility in this. Because if you view this naively, really you're not going to be making a lot of sense. And I'm highlighting this as well because I included a hierarchical aspect to this, which is important if you, for example, want to look at a global picture in this framework. But if you're wanting to look at more regional things, for example, having a higher number of clusters is important, where I'm also highlighting this because of the potential to move into an observational space after the next section. But NEMI is accurate, accessible, and interpretable, and a precursor of this was included in the New Zealand's Marine Protected Area legislation as applied to an ecosystem model. And I have a number of different projects of this that I'm very excited about. And in the future, I'm going to be moving to trying to reimagine how we think about emergent components of the system. And these are these low-order modes that a lot of the time we look at phenomenologically. So climate modes, for example, ENSO, and having and defining causal climate modes, I think is going to require a lot of innovation from the data science side, but also from how we just think about the system. And posing it as a graph, for example, could help us understand, say, the diversity in ENSO. I'm also very interested in the emergent structures associated with air-sea interactions. And being here, I think, would really allow a lot of really wonderful collaboration towards these things. And I have a couple of upcoming proposals on this. And now I want to jump into the second section here, so inferring subsurface circulation. But to just carry the data science portion of this audience with me, can remember the saying, don't judge a book by its cover. And really, from an oceanographic setting, that is incredibly true, because we have a lot of data from the surface, both from models like I'll demonstrate, and also from data, but actually going somewhere requires a lot of effort. So in situ, for example, you actually have to physically go there. So in terms of looking at something, just judging it from the cover, really you have to be very careful about this. So the grand challenge that I'm targeting is smart monitoring for climate and weather. And I mentioned that we're going to be using the CMIP data. CMIP stands for the Climate Model Intercomparison Project, short and snappy. And this is a really important data set. It informs world policy in terms of understanding climate. And it's a standard global data set of standardized emission scenarios. So how are we going to be moving into the future? And we have global modeling centers contributing to this, which is fantastic. Remember, I showed you that spread. We want to understand what this model uncertainty comes from and how we can deal with it in a constructive sense. But the fact that it's so big and diverse is also bad, because we're sharing over 20 petabytes of data from this whole ensemble, and there are just a lot to do with this data set. So while you have all the data as you run the model, really you can't even necessarily save, let alone share all the data. And for me as an oceanographer, because remember, these models take the entire Earth system into account, very often if I want to understand what the barotropic vorticity equations are doing, for example, that is really not information that's available to me, let alone, the 3D current structures even in a lot of these models. So we really need new metrics and methods, because this is really important. The ocean is a really important important component of the system. So now we'll be moving to the Atlantic after introducing the method, where I'm showing you one of the problems, or just a cartoon of it to the right, where we're looking at the change in the meridional overturning circulation, or the MOC, with abrupt 4 times CO2. And abrupt means that we release 4 times the amount of CO2 as is in the atmosphere, and then we look at what happens after about 140 years. That's what I'm going to be showing you. So this is really hitting the system with a very big hammer. And nominally, all the colored dots there are different models and how the model has changed in terms of what's happening with the new mean AMOC state. But really, all this tells me is that a lot of them, or most of them, are trending downwards. So the MOC is going to slow down, but not why. And why is what I'm interested in. So what we're going to do is fill in the missing data by predicting these dynamical regimes, these 6 regimes, where the grand challenge here, and this is a really hard problem, subsurface inference is a formidable problem in oceanography, but it's also hard because we don't have a labeled data set. Remember, that's really a bottleneck for oceanographic applications. But here, data science and supervised learning comes in and is fantastic, because neural networks are universal function approximators. So if it is possible to move from the surface down to depth, neural networks have the ability to show us whether or not this is possible. And I'm also going to be demonstrating a way to understand why. So what I was able to do with my background was to look at what data is available, and because I'm also interested in moving to observations, I stuck to data from the surface. And because I know what terms I need, I can pick data that really allows me to go back and look at the equation terms. So I can create a labeled data set. And then having the labeled data set, what you do is that you build a neural network that can predict the different dynamical regimes on the basis of the covariance space that they're querying in your input data. So the white dots there show you what's called nodes, and what you're doing is setting the weights and biases between them. So this is an optimization space. So we now train a neural network and are able to access these dynamical regimes for arbitrary models. And I'll be going into the architecture here in a little bit more detail in the 3rd component of my talk. But the method was one that I developed together with my collaborator at Zat, and it's called the Tracking Global Heating with Ocean Regimes method, or THOR. And we really went above and beyond to validate and make sure that we're able to open this black box, because remember, this is a formidable problem in many ways, but it's also a very exciting one. And I'm also very passionate about making sure and moving towards equitable computing, also beyond the centers like Princeton or GFDL, where we have access to data and expertise and also compute power. So just to highlight what Thor is doing, you can take an ocean model of interest, or any model that's of similar resolution, even an idealized one, extract this input, put it through this ensemble of trained multi-layer perceptrons, a type of neural network, and then find the most probable class for each latitude and longitude. So the fact that we have coherent patterns really in itself is extraordinary, because I tell us nothing about these types of things. And then we also chose this architecture because we have access to explainability methodologies through this. And I mentioned that we really go above and beyond here. This is one example where we train the network and tick all the data science boxes, but now I was able to take a completely unseen model. This is the CESM model that might be familiar to some of you, where I was able to get the barotropic vorticity equation budget closed very accurately. And this is I'm glossing over a lot of detail here, but closing this budget is really difficult. So getting this data was very exciting, where we can see that using Thor correctly identifies similar regimes, so we're happy to proceed with this. And Thor is accurate, accessible, and we can also explain it, and it's used to recognize processes and improve climate models both nationally at GFDL and also internationally at the FTSL lab. And I have a number of different exciting upcoming and also completed projects on this. But today I'm going to be focusing on the North Atlantic and the Atlantic Meridional overturning circulation, where to the right you can see a sketch of the circulation, or sorry, of the patch that I'm looking at, just to show you a little cartoon of what we can do. So the blue area is where we have these waters being carried across the basin in a cartoon sense, of course, the North Atlantic Drift or the transatlantic current. And on the the western side of the basin, we have the Gulf Stream that we can see through this layering of different regimes, and I'll be coming back to this. But just to highlight that under a climate change scenario, where we're going out of sample, we don't have any data from this area, we can't validate, so this is really important to look into carefully. I'm showing you data from the GFDL ESM model, and this is a stream function, which is a zonally averaged way of looking at the circulation, where to show you how we can interpret this, the red areas are areas of clockwise circulation, so these are these warm waters being brought north that then become dense in return. And if we hit the system with this hammer of 4 times abrupt CO2, what happens is this in the GFDL model. The AMOC really decreases, it doesn't reach us far north, and it's much weaker. So what's going on? And to understand what's going on, there are a couple of fingerprints we can look for that are recognized in literature, where if we move from a stronger overturning to a weaker overturning, the Gulf Stream nominally shifts north. I'm showing you that with this little red box on the cartoons. And we also have this current that moves across the basin, not reaching as far north, and sort of shifting east, so going from being nice and spread out to being much thinner. And the Gulf Stream is one that we're of course familiar with in this region, where what it's doing is that as it's moving up from here to around Cape Hatteras, it's pretty barotropic. And that's effectively depth invariant. So in the cartoon on the bottom there, you can see the flow and these white arrows, and of course I'm simplifying a lot here. But what happens when it separates from the coast is that it becomes more baroclinic or depth varying. So there's more of a difference between if I look at the surface and if I'm looking further down. And of course this has big implications for the basin scale heat content, which is something that I've also worked on and I'm very interested in. What does this have to do with the dynamical regimes? This is what I'm about to show you, just in terms of a very cartoon version. And if we now look at the different regimes here in the color, we have some areas that are more barotropic and some that are more baroclinic. And if I'm at the surface, on the shelf, then I'll be highly barotropic. But as I'm moving off, I'm becoming increasingly baroclinic. So the orange area is still somewhat barotropic, but more baroclinic. As we move into the green one, this shifts more to the baroclinic side, and then even more so until we reach this level somewhere in between, but certainly in the pink area, where in this model we're not really caring about the deep areas anymore. So remember the Sverdrupian regime, which is this pink one, we really don't have a lot of interactions with the seafloor being what's driving the circulation. So just to highlight this again as well, in a modern sense, we would, if we're looking at this with the dynamical regimes, see this dark blue area looking a little bit like a trumpet shape. And then if we move into a weakened AMOC state, this isn't going to be as vigorous, it's not going to go as far north, and it's generally going to be a little bit narrower or shifted east is another way of expressing that. Okay, so now we're getting to the exciting part, where we take 3 different climate models, 3 different of these IPCC models, and we extract the surface fields and then run this through a slower algorithm. And what you're seeing as a result here, we have the GFDL ESM model, one from the UK ESM, and then also this IPSL model. And these all, from the historical sense, look very similar, and that's great. That's sort of the first benchmark tick. You want it to look similar for the historical scenario. But now if we look at these runs from the increased CO2 forcing, things start to look very different. And I'm going to be zooming in first on this region, where if we look at this more carefully, you can see that in the historical sense, yep, we're still looking fairly similar, so doing well. But if we look at this 4 times abrupt CO2 increase, we can see that yes, most of them have shifted north in terms of the Gulf Stream because this orange area has really gone up, and we also have the blue area that's shifted up. So in that sense, there is agreement. But look at, for example, the UK ESM. It really has this blob of dark blue, for example, and how you parameterize interactions with the coast here is very hard and very important. So the model, how it reacts to this, is really very sensitive to this. And if we now look at the other aspect, this blue aspect, we can also see it's fairly similar in the historical sense, but then it becomes very different and really doesn't reach as far north. So now I can go in and say, okay, I know that all of these circulation patterns and the IMIC is weakening, and I can now go in and say, okay, what dynamics are actually associated with this? So I can go from just having dots to actually saying something about the processes. And in the future, I'm very excited about also saying something about, for example, developing targeted sampling for long-range weather, so weeks to months and extremes, where with a Thor-type methodology, having found these emergent patterns in different systems, for example, in terms of air-sea interactions, I think it would be incredibly exciting also to collaborate with people here to move towards actually making this more useful. So developing methods to actually sample in areas where we know we need more data, and that could then improve simulations. But I'm also very interested in the way that we make these forecasts more traditionally. So I'm interested in two different aspects of this, both data-driven, so looking at just data, and using new machine learning methodologies that can really harness things like GPUs. I have an ongoing conversation with NVIDIA. And also a completely physics-driven one, so more sort of classical, and building in machine learning to look at things like initial value problems and what areas we need to really look at in terms of the parameters. And here I'm looking at sea level, which I think one could also have very exciting collaborations here among the faculty. So now coming to the last section, I'm going to be talking to you about ensuring safe and transparent methods. And this really needs no introduction. I think we all agree, wherever we are, that using machine learning as a black box is something that really can be very problematic, certainly for high-stakes decision-making. So the challenge here is trustworthy machine learning, where I'm particularly interested in trustworthy machine learning for science. And I discussed this in a number of publications. And this is exciting because, remember, neural networks can solve formidable problems. They're universal function approximators. So if we manage to open this box, we can see why. And I think knowing why and knowing how uncertain the predictions are really going to be very exciting in the future. And this is something that I'm actively working towards, where using XAI, or explainable AI, that I'll talk about in a second, together with understanding how confident your neural network is, where I work with confidence scores, can really lead to this safe and trustworthy method, which I'll be demonstrating Thor actually is. So when you're training a neural network, what you're doing is setting these weights and biases. And for example, here I'm showing you the image of a cat, where we've trained the weights and biases. And what XAI is, it's called additive feature attribution. And this is a method that's causing some controversy in the machine learning community. It's actively under development, so this is good. And Thor uses a couple of different methods to look at different types of uncertainty. And what we can do is propagate what's called relevances backwards. And if you look at the heat map on the bottom left, you can see the image of a cat. The algorithm has successfully ignored the theme in the background, and we're just looking at the little ears and the little nose. So here I can now say, if I can recognize this, this can probably recognize a cat. But I'm not interested in cats or dogs, I'm interested in physics. So if we now return to this, we can do exactly the same thing. But remember, I engineered this data set to be interpretable in terms of neural network applications. So what I can do, for example, for the pink area in the North Atlantic, the spur drop region, is know that the wind stress should be very important, and that the depth should not be important, because remember, we're not interacting with the depth anymore. And looking at the relevances, this is exactly what I see. So in the blue areas for the H there on the left, the areas that are blue are actually areas where we have a very prominent piece of bathymetry. It's called the Mid-Atlantic Ridge. And this is where the network says, this is actively unhelpful. This is not, this should not be in this regime. I'm not going to look at this. And this is exactly what it should be doing. So in that sense, I can hard code this into the algorithm. But I've glossed over this. We use an ensemble multi-layer perceptron. And this is because if you look at the individual neural networks, so not ensembling, this looks completely wrong. The method fails, and you need to go back to the drawing board. But remember, this is a formidable problem, and that means that the latent space, or the covariance space that we're exploring, which is what a neural network optimizes. Remember, on the bottom, we're trying to search for this typical green line. So if we look at this, it's completely reasonable to think that when we're exploring this space, it's very rough, and if you were to try to optimize and find a way down, you might be ending up in what's called local minima, rather than the global minima denoted in blue there. So I'm just adding lines there on the bottom right, showing you where they might end up in the top. And what we're wanting to do with these different ones is really find this optimal solution, and we can do that if we ensemble. And I can verify that that's actually working using these XAI techniques. And that's really significant in the sense that I can actually demonstrate that the neural network reasons like a scientist. And that's what I want if I'm applying it out of sample in a climate change scenario. And I also mentioned that I'm very interested in confidence scores. And this is because the neural network is going to give me an answer, whatever. It doesn't care about uncertainty. But if I move into a framework that can actually deal with this, and this is what I'm interested in right now, is using Bayesian methodologies, because then I can move into having weights and biases actually being distributions. I can do things like calculate the entropy and say, okay, this is an area where the neural network is sure, it's seen this distribution before, it knows this. And areas where there's lower certainty, so where if you want to flag areas that you might want to look at a little bit more carefully, these are areas that flare up. So this is exciting for a number of different reasons. Of course, in terms of understanding how applicable and how much you should trust your result, it's important. But just to demonstrate the potential and what we can do here, if I look at just this red dot area, this is an area where we have a front, so it's interesting for a number of different reasons. And I'm showing you on the right what the network said about the different probabilities. So on the bottom x-axis we have the dynamical regimes, and the pink area was correctly picked out. But notice the adjacent area, this blue area, was very close. So what's going on here? And now what we can do is we can go in and reinterpret these explainability metrics by looking at what's actually happening. So here I'm showing you in this grid, the top row is this blue regime, the bottom is the pink. And if I'm now looking at these heat maps, I can say that yes, for the wind stress curl, both of these were both the dark blue and the pink regime thought this was important. Okay, so this is a little bit like if you're trying to recognize a cat and a dog, both of them have ears generally. But if we look at the sea surface height, another one of the inputs, we can see that this was more important in the pink regime than in the blue regime. And that's something that then you can go in and say, okay, the network is sure that there's something going on here in the covariance space. I should probably think about this more carefully. And in that sense, I think in the future, looking into how we can develop safe and transparent algorithms for science is really important. And particularly also because I'm interested in actual impact. And for actual impact, we need to make sure that what we're producing is fit for purpose, especially for high stakes decisions. So I mentioned that these XAI methods are under active development. There are a lot of boxes you need to tick in terms of applying them. And I also think that innovations around uncertainty quantification, for example, looking at uncertainty in the data as well as the network, is very important. And I have a number of different exciting projects on this. And I also want to mention briefly that this was just a small section of the work that I do. I also have an interest in ocean ecology, and here I've done a little bit of work looking at plankton ecosystems in the very complicated Darwin model, developing a new methodology, and looking at how connected different ecosystems are, how they emerge in different areas, and also how complicated a model needs to be to really be able to represent these. And in the future, I hope to also move into these, this using data here, particularly in situ, to look at things like the carbon cycle, but also sustainable fisheries, where I currently am writing a proposal on it. So to summarize now, I've shown you a data mining example using a different method, a different terminology here, where we saw that we could make fundamental progress in how we understand these equations, and I showed you an example of the super gyre framework that I've proposed for the Southern Ocean, and this was used. These methodologies were used in US and New Zealand policy. I've also shown you what we can differently call a sparse data inference problem, this inferring the subsurface. And here we were able to, guided by physics, create a data set and then also produce this subsurface inference methodology that's global, by the way. I just focused on the North Atlantic. And we looked at AMOC here, where the impact is that we're able to then understand the processes that are changing between different models and between different runs. And finally, I also showed you how we can show and make sure that a network is actually able to reason and have transparent predictions. And this is something that I'm also very excited about. But I want to end on a call to action here, where I think data science is here to stay, and we can really innovate very powerfully and really leverage the data we have. And I think this is great, but we also need to do this with caution and really make sure that our methodologies are fit for purpose. And with that, I thank you very much for your attention.
Questions from Maike? From the audience and from Zoom?
I have a question.
David?
So let's go back to like your barotropic vorticity equation. One equation I recognized.
Fantastic. Is this one okay?
Yeah, okay. Why is there a 0 on the left-hand side?
Sorry?
Why is there a 0 on the left-hand side?
Oh, that is because I spent a very long time closing this as a budget.
Mm-hmm.
So that is, for this application, also I think very important, because what I'm showing with using the k-means algorithm is actually that I'm able to make incredibly strong statistical assumptions, which, as someone that can put on a bit of a statistician hat, is a big leap. So I wanted to make sure that I actually captured everything in the data, and that's why I put a 0 there.
Well, I mean, okay, what would normally be there would be DDT, right? There would be like a d-zeta dt.
Oh yeah, I'm looking at the mean state, so I'm looking at
Okay, yeah, so basically you're diagnosing, I guess, a regime,
Mm-hmm.
right? But you're assuming that at any moment or maybe some block of time you're in some mean state.
Mm-hmm. Mm-hmm.
What was that averaging time?
So I use the echo data, so it's 20 years. And for the CMIP data, I also use 20-year averages. And I should also mention that this is something that I'm really excited about moving beyond in the future, where the NEMI methodology and the high-resolution regimes, where I'm really excited about starting to look at, you know, the mesoscale and different processes. I think we can move beyond, but we really just need to make sure to do this, that we're performing this data mining problem in a way that actually does the data justice, so it's not misleading. Because I think that we really need to make sure that everything for this type of application is present. Thank you, that's a great question.
We have questions on Zoom?
Can you hear me? I have a quick question.
Yeah. Go ahead.
Hi. Great presentation. I love that you use the Shapley and Thor methods for explainability. I think that's really, really helpful. I was wondering if you've tried Bayesian inference to try to quantify the area or kind of range of predictability for these ML models. And if so, what your thoughts are on whether that is an effective way of trying to increase explainability.
That's a great question. I have a student starting with me this summer. He's one of the Holling scholars, and we're hoping to actually look into those types of questions in a little bit more detail. So I appreciate that question. It's a great idea. The answer is not yet.
Great, thank you so much.
Manish?
Yeah, it's super cool stuff. I'm kind of wondering if you just like took a model and calculated those terms in the barotropic vorticity equation. I've seen studies that do that, and you get, at least for the regions I'm familiar with, pretty similar distributions. I was like, what does like Thor tell you that you get from like not just calculating the vorticity terms?
Well, you get so I think a few things there. For Thor, we engineered this specifically for seamen. And to close the barotropic vorticity equation in MOM6, for example, the model that I'm working with now, you need at least 39 different terms for each grid box. And imagine you can't really share all that data for the different seamen models. So that's one thing that I would say for Thor specifically. But in general, if you say we're just averaging over a streamline, so some of the really nice work that's come out lately is from Schonhofer, for example, or Le Koch, and there they either look at the one spirit of streamline, which is what I was showing you, or just sort of take slices of the different area. And doing this is a much more sophisticated way because we're actually with statistical rigor saying this is the boundary between this area, this is the boundary between this other area. But I'm not saying that the other ways of doing this aren't useful. I'm saying that this is objective, and this is rooted in this appreciation of the fact that within this space you might have unexpected things, like the Southern Ocean regime is not something that you arrive at using this existing knowledge, as I call it. So this is really an objective way of dealing with this that we can really lead to insight.
Makes sense. Cool, thank you.
Arthur?
Yeah, last statement you made in your talk about knowledge-based. I was just wondering, in the state of the art in neural networks, is somebody going in there trying to replace these sigma functions, say, with dynamical basis functions? That's the worst thing I think about neural networks is we know in many systems what the basis functions are, at least in a linear sense. Is anybody trying to put those in and fit them?
Not to my knowledge. I mean, some of the things that are happening that are exciting but potentially a little bit complicated for the ocean is that people are using Fourier decompositions, for example, which in the atmosphere, fine, but we have boundaries. And there are also different ways of constraining what's called the loss function, so how you sort of bring everything together at the end. You can put some equation terms in there, which of course sort of constrains things, but only at the end. So for me, those aren't super satisfying, but I think there's really a lot of scope for innovation.
With deep learning, it's possible to build prediction models by just training it on large data sets, very much like ForecastNet, for example. And it's possible to build deep learning emulators of components of models, say subgrid-scale physics.
Mm-hmm.
Do you have an opinion which approach has a more prosperous future?
I guess it depends on what you mean with prosperous. So I think there's scope for both of them, and I think, and ideally, the two of them would learn from each other. So effectively, what we're doing with the completely hands-off approach that you take when it's completely data-driven, like ForecastNet, there's also a new one called GraphCast actually that does a little bit better, and the methodologies they're using are also very interesting. But what's happening there is that they're really targeting sub-seasonal to seasonal predictability, which is a little bit of a different ballpark in terms of what the sort of core parameterizations using machine learning are targeting. So the efforts that I'm aware of that I think are very exciting are, for example, trying to replace GM in these models, which I think I think is certainly worth following. I'm not sure if life cycle for the NVIDIA effort, for example, one would hope that NVIDIA still cares about this, decades down the line. But of course, this is not government sponsored at this point, so there are a couple of different ways you can look at that.
I have a question. It seems to me that most of your applications started from model data, and with Echo, the model data has seen observations through its own data simulations. Have you tried applying these things directly to observations?
I would really like to do that in the future. I think for me, moving into the real world space is really exciting, and I see starting in models as sort of a way to hierarchically move up to that. So in two proposals, I have the one on sea level for these more traditional sub-seasonal to seasonal forecast models. That's the ultimate step. But also for Thor and a lot of the future work that I explained, I think it's geared towards using actual observations. And there I think there are a lot of challenges that we need to overcome. And one that I think is incredibly exciting is that we need to be able to validate in the real ocean for things that we haven't seen yet. So I can take the Argo data, for example, but the Argo data, for example, bends in depth. What happens between them? Is that something that I accidentally introduce as a bias in my model? I'll need to check. And in that sense, I think there's really a lot to learn also from going into the real world. But I think starting with real world data has a lot of challenges associated with it. So this is something that I'm also actively looking at. Actually, the student Yvonne Yenning is looking at the comfort data set, and this is a data set that has a lot of, she's very interested in the biogeochemical aspects of this. So we're trying to find ways of both imputing the data, so filling in missing values, but also move, when we've done that, because that's also a big problem, when we've done that, try to figure out how to scale data mining methodologies towards dealing with this data, because this data is very different. It has a lot of noise, which could be a signal. It has a lot of, it's incredibly imbalanced because, for example, if you're looking for something in the North Atlantic, you have a lot more data than you have, for example, in the Southern Ocean. So there's just a lot of different considerations that you need to take into account. But it's a very exciting space that I'm happy to be in.
Any other questions from the audience? The Zoom audience is quiet? All right, let's thank our speaker.